Welcome to this module. In this module, we will go through the advanced thermodynamics for life cycle analysis, where we will be looking at the role of second law of thermodynamics, and then we will go through some of the fundamentals of exergy calculations. So, just a quick recap, when we did the energy analysis, we make a simple energy flow diagram that tracks the energy inputs and outputs for a process or for the life cycle, and you have the feedstock processing energy as the input and the product and waste as the output. So, we can definitely look at the improvement of these processes if we know the fuel output, if we know that if there is actual energy output from the product, but if there is not that, then we can only calculate the energy required per unit product. We cannot understand where the losses are actually occurring or what are the efficiency improvements that we can make for the process. So, for that what we go is we use the second law of thermodynamics. What second law of thermodynamics says is that during any natural process, the total amount of entropy in the universe always increases. So, that means that if you have a process that has a decrease in entropy, then there must be an equal increase in the entropy outside or in the environment. And at equilibrium, after which there is no change, entropy is maximum. So, these statements might seem little vague right now with the connection to sustainability, but you will see how it gets connected. What it leads to the calculation of the quality of energy or the quality of product, because it tells that how much of the energy is there in that system that is actually available to do work. So, whenever we are thinking about a product or the life cycle or the process that is making something, what we are really concerned about is how much energy is actually being utilized to give the useful output. So, the available energy is what we are concerned about, and that is what comes from the law of second law of thermodynamics, where we know that all the energy available will not be converted into work and there will be some entropy in that generation process. So, to do that, we will start with simple definitions that we can use for the calculation of these relevant values for the implementation of exergy analysis. So, to start, we talk about what we call as state functions, and state functions are a property of system at equilibrium, that is a property depending only on the current state of the system independent of how that state was achieved. For example, if we have a block that we raise up to certain height and it gains certain potential energy, then we only calculate the potential energy as mgh. We do not care about whether that block was brought at that height through a curvaceous path or straightforward path, or through a pulley system, or through someone actually putting the block up on that height. So, this is what is the state function, because you are only concerned about the initial state and final state. So, similarly, when we have to look at the quality of energy or the quality of available energy, for all the inputs in our LCA model, we can define them in terms of state function, which can be used to study the changes without worrying about the details of internal processes in the life cycle stages. So, we can understand the input and output state function, and we will define those state function in terms of exergy, and that can be used to do an exergy analysis that gives an idea about how good the process is in utilizing the available energy for conversion into useful product. Next, what is entropy? So, entropy is defined as another state function. It is given as ds equal to dq by T, where you have dq is the heat transfer and the temperature is at the temperature at which the heat is being transferred. For all irreversible processes, your ds is greater than 0. What that means is that if you have any process that takes in heat to create a product, there will always be some losses. So, some processes may be more efficient at utilizing it, and some processes may be less, because your ds is always greater than 0, which implies that you cannot convert all heat to work, because it is hard to get a completely reversible process, and there is always some generation of entropy in that process. And that brings us to the concept of the quality of energy or available energy. So, whichever you have, whether you have a heat or a material flow, we can understand how much is the, for a heat flow, we can understand what is the quality of energy or available energy, because we know that when that heat is transferred to do work, there will be always some losses. Generally, your heat at higher temperature is of higher quality, since you can get more work done from it, and there is always a reference system that we use. So, you calculate the actual work done by T minus T naught, where T naught is your reference system. And if you have taken a thermodynamics course, you might be aware of the Carnot efficiency. That is what is known as the Carnot efficiency, where it will it depends on the temperature gradient, and there is always some losses that happen. So, coming to the term exergy analysis, and I will not focus on general second law of thermodynamics, but mostly just on what exergy is and how we are going to use exergy for our sustainability assessment. So, yeah, do not, this is not a comprehensive theory of second law of thermodynamics. This is more focused on just exergy calculation. So, here, because we are interested in calculating the flows or the thermodynamic implication of each of the flows in our life cycle model, what we are concerned is with available energy. Since not all heat can be converted to work, we know that the actual capacity of doing work is different for different heat flows. Similarly, we'll in a while we'll also see how we define the exergy for a material flow. But in just the basic definition for exergy is the maximum amount of work that can be done by or on the system with respect to a reference state. So, maximum work is done when a system is brought in equilibrium to a reference state, and that is what we define as exergy. So, in a simple terms, we can think of exergy is that if we have a system, let us say at temperature T, and we are going to bring it to in equilibrium with a reference temperature T naught, then that is the whatever the maximum work that we can do with that heat flow at that temperature is what the exergy of the heat flow is. So, that gives us an idea that if you have different flows in a process, then what is the quality of work done or quality of product that can be made using those flows. Distance from equilibrium. So, this is another important concept, because we are thinking of putting the system in equilibrium with some reference. So, a system, if it is in equilibrium with the reference system or surrounding, it cannot do work. So, in that case, of course, your exergy will be 0, because we cannot extract any work from that particular stream. Another way to think about it is that maximum amount of work that can be done by the system when it is brought to equilibrium with its surrounding is exergy, and then as system is at equilibrium, that is when your exergy is equal to 0. So, as we go forward in the module, we will see some examples of exergy calculation and it will become more clear, but for now, if you can just keep this concept in your mind that exergy is the maximum work that we can extract from a system when we bring it to equilibrium to the reference state is what is exergy, and when it comes to equilibrium, then your exergy is equal to 0. So, let us look at the equations that we use for calculation of exergy in different disequilibrium scenarios. So, when we imagine processes, there are different things that happen. There is of course pressure and temperature, that is an important gradient that is there in driving the processes. So, let us say if we have a ideal gas system or a gas stream that is entering your process, then exergy due to, and it can be at a different pressure. So, if your gas is moving from pressure P to P naught, then the exergy of the gas system will be, if it is following an ideal gas behavior, is minus nR T naught integral of P naught dP by P. Here your T naught and P naught are the reference temperature or reference temperature and reference pressure. So, whenever we are defining the exergy, we also define a reference state with which we are calculating the exergy. And now, when this reference state is the same as the environment, which means that your system is going to come into equilibrium. So, by definition of exergy, we are calculating exergy is the work done to bring the system in equilibrium with the surrounding, that is the maximum work. So, here we are bringing the gaseous system in equilibrium with the P naught, which is the reference state or the surrounding, and the initial pressure of the gas was P. So, using the equation, now we can say that your exergy for an ideal gas system, where N is your number of moles, is given by nR T naught ln P by P naught, where T naught and P naught are your reference. So, T naught is your reference temperature and P naught is your reference pressure. The next thing is temperature gradient. So, you might come across processes where you might have different temperature of the streams that are entering your processes that are included in your LCA analysis. So, here you have temperature gradient and that causes some gradient that causes some work done that can be extracted from it when that stream is brought in equilibrium to the T naught, which is your reference temperature. So, here your exergy is given by the change in enthalpy and the change in entropy. So, whenever the temperature of the stream will change and there is constant specific heat Cp, we can say that there will be change of course enthalpy. So, at temperature T your mCpt is the content and minus T naught is your temperature gradient. So, your delta H is mCp delta T. And then also the change in entropy, because the higher temperature may have higher quality and with the lower you have a less work done available and more entropy. So, you will have minus T naught S minus S naught. So, this is a simple example or simple equation that you will use if you know that you have streams that are going to be at a different temperature and what is the exergy content of those streams that are entering in your flow system or in your LCA system based on the temperature gradient. The next component that will contribute to exergy or the available energy is the concentration gradient. Here you have let us say you have a stream where you have different gases and they have mixture, then you can calculate the exergy of mixing for an ideal gas with composition Xi0 to form a mixture in which its partial fraction is Xi. So, Xi0 was its molar fraction in the reference state and now you have mixed it and the molar fraction in the mixture is Xi. So, your exergy for this system will be summation of I nR T0 Xi ln Xi by Xi0, where T0 is the reference temperature, Xi0 is the molar fraction in the reference state and Xi is your molar fraction in the mixture. So, that is how you can calculate the mixture exergy if you have a stream that has a mixture of gases entering into the LCA system. If you have a single compound that and it is present in the same form in the reference environment, then it is simply given as minus nRT0 ln x0. So, these are some simple examples or simple expressions that are used for calculation of exergy in different stages. So, the first one is of course your pressure gradient. So, whenever you have a process, you might have streams that are at different pressure than their reference state. So, in that case what we mean is that the exergy is the amount of work that has been done to raise the pressure of that stream. So, let us say I have a process and I have a stream that is entering at pressure equal to 2 bar and let us say it has some temperature equal to 200 degrees Celsius. So, now what this stream will have some exergy by the fact that it is at a higher pressure and at a higher temperature, which means that there was some work that was done to actually raise the pressure and temperature of this stream, and that is the thermodynamic contribution of this stream to the process. You can have another process, and in that case your pressure may be actually 3 bar and let us say temperature is 50 degrees Celsius. So, the exergy of this stream will be very different than exergy of the another stream. So, when you are doing a comparative analysis using the second law of thermodynamics, then you would be understanding how much energy has been or how much available energy has been spent in actually preparing the streams that are input to your process. So, this gives an idea of how we do the temperature gradient and pressure gradient, and also it might be a mixture of two gases, and then you can use this formula to calculate the exergy due to concentration gradient, or how you have brought the system mixture into formation, that is the input for your process. So, let us move forward. So, now we are thinking of exergy for steady stream of matter. So, as I said that we can have different streams that are entering and leaving the system, and in the exergy analysis process what we are interested in is, we are interested in calculating the exergy of all of these streams. Okay. So, now let us think what are the components of different exergy that is part of these streams. So, exergy, as we know, is the available amount of work or the quality of or the available energy in the stream. So, you can have a kinetic, potential, physical and chemical. 4 components of exergy forms part for any steady stream of matter that you can consider in your LC analysis. So, kinetic is simply because of the motion or the flow. Because of the kinetic energy, you can also convert it into the work, and of course, when you are giving certain velocity to the stream, you are doing some work to raise that kinetic energy. Hence, that delta is giving you how much work or available energy has been spent to prepare the stream at that flow rate. Similarly, the potential, if you have some height, physical and chemical we will quickly see. So, exergy of the steady stream of matter is equal to the maximum amount of work obtainable when the stream is brought from its initial state to the dead state, and the dead state we mean it's in the equilibrium with the environment or the reference state, and it is by processes during which the stream may interact only with the environment. So, it is not mixing, otherwise it is just interacting with the environment. So, let us reflect a little bit on this definition. What it means is that when we are preparing a stream that is entering our LCA system or processes, we are doing some work, and that work is the exergy. It is calculated in the reverse form by saying that if I have to bring this stream back into the dead state, which is in equilibrium with the environment, how much work I need to do or how much work has been done, and that is the available energy or exergy. When we calculate that, indirectly we are saying that this is the amount of available energy or work we need to do to prepare the stream for our system, and that is the quantification using second law in terms of thermodynamics metric for the process. So, for calculating exergy of streams in the process, when we do analysis for our LCA or other process analysis, we ignore the kinetic exergy and potential exergy, because generally the input and output will be, the flow rate will be same. So, your steady state flow is maintained. So, we do not need to worry about that, and generally the processes are at approximately same height. So, you do not even need to worry about the potential exergy change. So, what we are interested then is only in the physical exergy and the chemical exergy part of the streams. So, now we will look at the physical exergy and chemical exergy formula. So, keep in mind that we have already seen that there are 3 different gradients that can be used for calculation of exergy. So, the temperature part, the pressure part and then the concentration part, and we will see that your physical and chemical will have contributions from different parts of these gradient. So, before we go there, I would like to define some of the states that are used for calculation of exergy. So, initial state is actual state of the stream you are considering. So, it can be the temperature and pressure at which that stream is being used in your process. Environmental state is the one that is achieved in restricted equilibrium, and substances of the system are restrained by a physical barrier, which means there is no mass exchange between system and environment, and it reaches equilibrium in temperature or it reaches equilibrium with the environment in terms of T naught and P naught. So here only energy flow is happening and the pressure equilibrates as well, but there is no mass exchange. So this is where we call it the environmental state. The last state is the dead state. Dead state is where we are making the system in an unrestricted equilibrium, where you achieve mechanical, thermal and chemical equilibrium all together. So here you have a full thermodynamic equilibrium between the system and the environment, and then your system cannot undergo any further changes when it is in contact with the environment, and that state we call as T00 and P00. So the difference between the environmental state and dead state is that dead state is, let's say we have an environment and we leave any stream, it will undergo, the chemical species that are there may also undergo further degradation, that it comes in the chemical equilibrium as well. So in this we only have the physical and thermal equilibrium in terms of pressure and temperature, but here we also achieve the chemical equilibrium, which is an additional step. So when we calculate the dead step, we always look at the reference species that are available in the environment, and when we do an example you will see what we take as the reference species for calculation of the exergy based on the dead state. So let's go and look at the physical exergy of streams. So here physical exergy is equal to the max amount of work that is obtainable when the stream of substance is brought from its initial state P1 T1 to the environmental state P naught T naught by physical processes which are only involving thermal interaction with the environment, and also these are reversible physical processes. If you have irreversible processes, there is further loss, but we are looking at the reversible physical processes, and we are saying that we are making the initial stream which was at P1 T1 in equilibrium with the environment. So when you calculate the physical exergy for this, now here what you are saying is that you have a pressure gradient, so you will consider the contribution of pressure gradient, and you also have the temperature gradient, so you will consider the effect of the temperature gradient. So here our EPH will have Cp T1 minus T naught is the enthalpy change, and then the entropy, so minus Cp T naught ln T1 by T naught. So that gives us the temperature contribution to our physical exergy calculation for a stream. And the next one is our pressure contribution, which is T naught R ln P1 by P naught. So we have independently seen the pressure gradient exergy calculation and the temperature gradient. Here when we are considering the physical exergy for a stream, we combine the both, because in this the definition of exergy is that it comes into equilibrium with the environmental state in terms of P naught T naught. So you are dissipating the pressure gradient and as well as the temperature gradient. So whenever you are calculating physical exergy for a stream, remember that you need to pick a reference state which is your environment and pick the T naught and P naught for that environment, and then you need to contribute or add both the temperature dissipation contribution and the pressure dissipation contribution to calculate the total exergy. So in review, physical exergy has both the thermal component and pressure component. Your thermal component is the ability to do work due to temperature difference with the environment. Pressure component is the ability to work due to pressure difference in the environment. And thermal component is very similar to heat exergy. So we have talked about heat exergy, that whenever you have an heat exergy transfer, there is some exergy or the work available in that particular state. So now that we know how to calculate physical exergy, what we will do is we will do a quick problem to calculate the physical exergy. So here in this problem, you are asked to calculate the specific physical exergy. Whenever you see a word of specific, that means that you are doing per unit mass. So we are going to calculate the specific physical exergy for air for a state defined by P1 equal to 2 bar and T1 is 393, which means that you have a process that needs a heated air for its system. So, and at a high pressure. So, you have raised the pressure and your environmental parameters is 1 bar and T naught is 293. The Cp of the air which contributes to the enthalpy or the heat component is 1.0 kilojoule per kg Kelvin, and you are assuming the air to be perfect gas. So, you are going to use the R as 0.287. So, take 30 seconds and let us quickly calculate the physical exergy and also separate the thermal and pressure component. Okay. So, let us look at the solution. We have the equation as Vph given by Cpt1 minus T naught minus Cpt naught ln T1 by T0, which is the thermal component, and then you have the pressure component. So, when you substitute the values, you will have total value come out to be 72.29 kilojoule per kg. So, if you calculate the thermal component or the pressure component separately, that will come out to be 58.33 kilojoule per kg. So, following this approach, you can quickly calculate the physical exergy that is there for any stream that is entering the system at a raised temperature and pressure, and if it follows an ideal gas behavior. So, let us move forward and look at the chemical exergy. So, as it might be evident, chemical exergy is related to the chemical composition of the stream. So far we only considered the physical aspect of temperature and pressure. Now, for the chemical exergy, we can look at the chemical composition. So, by definition, chemical exergy is equal to the maximum amount of work when the substance under consideration is brought from the environmental state to the dead state. So, now instead of just moving from the initial state to environmental state, you are moving the system all the way to the dead state, so that it comes in complete thermal and chemical equilibrium with the environment. So, alternatively, we can say it is equal to the minimum amount of work that is necessary to synthesize the material and to deliver it in the environmental state, the substance under consideration for environmental stasis by means of processes involving heat transfer and exchange of substances only with the environment. So, yeah, I understand that is a big definition, but let us break it down. So, it is the equal to the minimum amount of work that is necessary to synthesize and to deliver in the environmental state. So, what you are doing is that you are bringing material from the dead state, which is complete thermal equilibrium or chemical equilibrium in the environment. You are synthesizing material and you are bringing it to the environmental state, that is, and you do some work in that process, and that work that you do is the exergy of that material. So, when we do this calculation for the species for which we do not have the exergy available, you will see that we take materials from the environment, we make it go through some reaction, and then we calculate the exergy of the material based on that it is now at a different state than it was in the complete thermal and chemical equilibrium with the environment. So, when you look at the chemical exergy, you have the difference between the initial state and final state. Your environmental state is equal to the environmental pressure and temperature. So, whatever reference state you will pick as P naught T naught, and your dead state is when you have the pressure, temperature and chemical potential. So, you do not have any gradient of the chemical potential as well in the environment now. So, that chemical potential of the stream is also equal to the environment, so that the stream can go no further changes, that is there is full thermodynamic equilibrium. So, that is the dead state that we define for calculation of the chemical exergy. So when you calculate when you calculate the chemical exergy, you also need reference substance. So remember that the idea of calculation of chemical exergy is that we need to bring the material completely to the dead state, which means to the complete thermal equilibrium with the environment. So if it is going to come to the complete thermal and chemical equilibrium to the environment, then you need a species with which it is coming in equilibrium with. So which means that you need to have a reference substance in the environment that you use as the basis for calculation of this exergy. So here, that's why we say that the property of the chemical substances in the stream must be referred to properties of some correspondingly suitably selected substance in the environment. For example, if we need to calculate carbon, so if we have carbon in our material stream, then we can use CO2 as a reference substance, because we have the CO2 in our environment. So whenever you have carbon, it can combust and it can come in equilibrium with the CO2 in the environment. So you have a reference substance with which there can be a chemical potential equilibrium that can be achieved for that species. Similarly, so you might have multiple choices to select for your reference substance, and mostly we use the lowest chemical potential for calculation of the exergy. And the reason being is that there is a tendency of the chemical substances to come in chemical equilibrium when they are left in open in the environment. So there will be always this dissipation of chemical potential gradient. So if you have something which is even lower chemical potential, then your substance will further undergo some transition to get to the chemical potential equilibrium. So you do not actually achieve complete thermal equilibrium or complete thermal and chemical equilibrium if you do not pick the reference substance that is the lowest chemical potential. So sometimes you will also come across your streams that might have component in which does not have a reference substance that you can use for the constituent element. For example, you have methane. For methane, you can use reference as CO2 for carbon and H2O for hydrogen. So if you have to calculate the exergy of methane, you need to use two reference substance, because carbon in the methane will come in chemical equilibrium or potential gradient dissipation with CO2, and the hydrogen in the methane will come in chemical potential equilibrium with H2O in the environment. So based on what is the constituent or the chemical constituent of your stream, you will be picking the right reference substance to calculate the exergy. So this is of course becomes a tedious process, because your stream may have multiple compounds and you need to pick the reference substance for each of that to actually get the exergy calculation. So for the reference substance, so let's say you have a reference substance, we also need to know the exergy of the reference substance itself, because when we calculate the exergy of let's say a compound and we write a balance equation to calculate exergy, we will need the exergy of the reference substance. So for calculation of the reference substance exergy itself, we use the initial state as T0 and P0 and the environmental state. The reason we take the initial environmental state as our initial state, because this is the reference substance and it is already existing in the environment. So its initial state is T0 P0, and we want it to get into complete thermal and chemical equilibrium so that it becomes dead, that it cannot undergo any further changes. So for that, your final state will be your T0, because you are not changing the temperature. So there is no temperature gradient because it is still in the same environment. But what may happen is that because of the chemical changes, you might have the partial pressure as the reference for that final dead state. So whatever component you are considering in the environment, the final reference would be the partial pressure of that in the dead state. And the idea of calculating the exergy of this reference substance then is the reversible process of bringing the gaseous component from P naught to P00. So, when it comes completely at the partial pressure in which it is naturally existing in the environment, then there will be no further change that will happen, and that is your exergy calculation, or that is the amount of work done to bring that substance into the complete equilibrium, which gives us the chemical exergy. So, for a reference substance, if you have a standard gaseous substance, your molar chemical exergy can be given by R times T naught ln P naught by P00, where P naught is the initial state of the reference substance, which is the environmental state, and P00 is the dead state or the partial pressure of that reference system, after which there will be no further change in the system. So, your molar chemical exergy for any gaseous reference substance in the environment is pretty straightforward, because you are only considering the pressure gradient change, the temperature is already the same. So, let us do a quick example on calculation of chemical exergy of reference substance. So, take 30 seconds to actually do this problem. So, let us look at the solution now. So, the molar chemical exergy of CO2 is, it's a reference substance because it is existing in the atmosphere already. So, we can use CO2 as a reference substance. The pressure is 1 bar for the whole air, but the partial pressure of CO2 is 0.0003 bar. So, when you calculate the molar chemical exergy, it is simply 8.3144, which is your R, and multiplied by 298, which is your temperature, because the temperature stays constant. And what happens is that this is generally just getting in the pressure equilibrium with the partial pressure of the CO2 existing in that atmosphere. So, you have 1 by, so P0 is your initial state, which is the environmental state, and P00 is your final state, which is the dead state for calculation of molar chemical exergy of CO2. So, the value comes out to be 20,108 kilojoule per kilomole. For molar chemical exergy for O2, we have the similar process. Here the partial pressure of oxygen is 0.2040. So, we just substitute the partial pressure in the denominator, and you have P naught, which is the initial state, as 1 bar, and we calculate 8.3144 into 298.15 times ln 1 by divided by 0.2040, and that comes to be 3940 kilojoule per kilomole. So, next, so that is the reference substance. Let us look at the calculation of chemical exergy for places where we do not have the reference substance. So, for example, most of the fuel substance do not form part of the system of common environmental substance. For example, methane. So, we do not have methane already existing in our atmosphere, and methane is most of the time inputs to lot of processes, and you might have some other processes as well, or some other streams as well. In this case, what we do is we need to figure out and pick a reference substance for each of these atoms. So, for carbon we will use CO2, and for hydrogen we will use H2O. Once you have that, what you will do is you will write an equation that actually creates that substance from the reference substance. So, what we are considering is that for this element or this particular fuel to be coming into thermal chemical equilibrium or thermal and chemical equilibrium with the environment in the dead state, it has to transform into one of the moles or one of the components of the reference state itself or the dead state itself. So, since CO2 and H2O, water vapor, is existing in the environment, if it has to be brought to the dead state, it will come in equilibrium with CO2 and H2O. So, what you would need to do is you would need to write equations or the reactions that will convert your methane into CO2 and H2O. To write that, you would need the Gibbs energy of formation for these molecules, and then you would write the balance. We will see an example. So, for example, we will look at the example of calculation of exergy for carbon monoxide. So, most of the waste streams that are eliminated or emitted from most of the processes also contain carbon monoxide. Now, carbon monoxide is not a reference molecule because it is not already existing in the environment. So, what we need to do is we need to calculate the chemical exergy of CO. The way it is defined is for the chemical exergy of carbon monoxide is the maximum amount of work that is needed to bring carbon monoxide to equilibrium with reference substance in the environment. Now, we know that we want to bring it to equilibrium with reference substance in the environment. So, for carbon we will have carbon dioxide and for oxygen we will have oxygen, which means that we will write an equation, a reaction equation that converts your CO2 with CO2 to CO and use oxygen. So, here this figure is mainly explaining this whole process of calculation of chemical exergy. So, remember that we want to calculate the chemical exergy of carbon monoxide, and it is at the starting point is P naught T naught, which is the environmental state, but it has to be brought to the dead state. So, our dead state is what? Our dead state is oxygen, and oxygen is at POO or the partial oxygen pressure, and CO2 is at the partial oxygen partial pressure of CO2 in the environment. So, the CO will need to equilibrate with CO2 and O2, and that is when it comes to dead state. So, how does that happen? So, for that what we would need is that you will first need to bring half oxygen, half molecule of oxygen, and it is brought into the system at T naught and partial pressure O naught, and then you raise the pressure. So, once we raise the pressure of oxygen to P naught T naught, then it can go into this equilibrium, which we call as the Van 't Hoff equilibrium box, where all this conversion is happening. So, it is kind of an imaginary box where you are doing this conversion. So, you bring this half molecule of oxygen, and then we write this equation. So, the carbon monoxide at P naught T naught reacts with half molecule of oxygen at P naught T naught, and it gives CO2. And the idea is that it will give you CO2 as the pressure P naught T naught. So, now what we have done is we have brought the reference molecule oxygen, did some work to it so that we raised its pressure from P00 to P0. So, there is some work that has been done. So, this shaft is basically showing you that there is work done. After doing this work, you put it in the Van 't Hoff equilibrium box, and then you see that there is some reaction that needs to be done to convert your CO to CO2, so that it can come in equilibrium dead state in the environment. And for that also there is some work done, which is your negative of delta G naught, which is the Gibbs free energy which is released when this reaction happens. It can be, if it is endothermic you need to do work, if it is exothermic it will release or it will do work, and also that is also connected to the shaft. So, that is the work done, so which contributes to the molar exergy of the carbon monoxide. Now, we cannot bring CO2 completely to the dead state because it is at the P naught. So, now we have to further reduce its pressure to partial pressure of P00. So, now what we are doing is we take CO2 that is created by reacting your carbon monoxide with half O2, and we put it through the reduction of the pressure, and it reduces to the partial pressure of CO2, and then it can be emitted into the environment, because once this CO2 stream is at the partial pressure P00, then it can come into complete thermal and chemical equilibrium with the environment. So, that is the definition of exergy, and all this work done in this whole process is what will give you the molar chemical exergy of carbon monoxide. So, in brief, what we are doing is we are trying to bring this molecule into dead state with the environment, but since this molecule is not in the reference substance in the environment, we pick one of the reference substance like CO2 and another molecule O2, so that we can use those two to write a reaction that can convert CO to CO2 and bring it to the dead state. And in all of this process, whatever work is done, so for example, work done to raise the pressure gives energy delta G, that is the energy released, and then the work done to reduce the pressure or work done by the turbine when the pressure is reduced, all of that contributes to the epsilon CO, which is the chemical molar exergy of carbon monoxide. We will also see this with the numerical example. So, let us do this problem. So, I will quickly go through this equation. So, here what we need to do is we need to calculate the molar exergy of carbon monoxide. So, now for calculating that, as we saw in the want of equilibrium box, we will be running this reaction, which is carbon monoxide reacts with half molecule of oxygen and gives CO2. And during this, of course, you will have delta G of reaction that we can calculate. The balance of the exergy is that your exergy of CO2, which is the output product, minus half exergy of the B oxygen is the exergy of the oxygen molecule, and you need half of that, minus B of CO is going to give the delta G reaction. So, your delta G reaction is basically the balance of all the exergy components that are involved in that reaction. So, using this equation, we can quickly then write then expression for BCO, which is the exergy. So, your B carbon monoxide can be written as BCO2 minus half BO2 minus delta G reaction. Okay. So, now all we need is to calculate the, so BCO2, because it is a reference molecule and we had just calculated its value, we can use it as 20 kilojoule per mole. B oxygen can also be used from the previous calculation, and lot of these reference substance exergy is available in the literature. If it is not available, you can use the formula to calculate it. So, B oxygen is actually about 3.9. So, this will be about 3. And for delta G reaction, we can calculate delta G reaction as Gibbs free energy of formation of CO2 minus Gibbs free energy of formation of carbon monoxide and minus half Gibbs free energy of formation of oxygen molecule. So, this value is minus 394 minus this is plus 137, and since your oxygen is pure molecule, you have 0. So, this value comes out to be minus 257 kilojoule per mole of CO2. So, for each of the mole of CO2 being formed by this reaction, we have the delta G of reaction is minus 257 kilojoule per mole CO2. Now, we can just substitute these values. So, you have 20 minus that will be approximately 2, 3.9, I am taking it as 4. So, that comes out to be 2, and then you have minus 257. So, this comes out to be about 275 kilojoule per mole of CO. So, you can see that the exergy of carbon monoxide, so you can see that the exergy of carbon monoxide is very high, and the reason being is that it is not a reference substance. So, you need to actually bring it down to the reference substance. So, using this process, you can calculate the molar chemical exergy of any fuel or any compound that is entering in your stream and that is not part of a reference system. So far we have learned calculation of physical exergy, chemical exergy for reference substance and for compounds. Last is mixtures. So, next thing that you encounter in any system that is flowing is mixture. So, when we think of mixture, what happens is that of course there is the chemical exergy of each of the component, but when you are bringing it together, when you are mixing, you are doing some additional work so that the things are together. So, chemical exergy of a mixture is the sum of molar chemical exergy of constituents. So, you will have all the constituents component and then the work done to bring the mixture together reversibly. So, if you have n components and then pressure of ith component in the mixture is Pi, and the work done is calculated as reversible work done to separate the compound. So, instead of bringing, you can think of also separating. Since it is reversible, we are able to say the work done in the both sense are equal. So, the work done is calculated as reversible work done to separate the components and compress it from partial pressure to the environmental pressure P naught. So, here all the components were in the environmental state and then you bring it together at partial pressure. So, you do some work. So, whatever work you will need to do to separate that component and bring it in equilibrium with the environmental state is what is the exergy of the mixture. So, it is very simply you can think that you are just putting things together and you are doing work. So, there is of course some exergy of the components itself, the molar chemical exergy or those, but then there is also some exergy in that mixture because of the fact that you had to do some work to put it all together in that different state than the environmental state. So, the example or the formula for this is very straightforward. So, your first part is the contribution of each of the components. So, you have each of the component has molar chemical exergy as epsilon OI, for where I is the ith component and Xi is the mole fraction. And then the second part is basically where you are doing some work to bringing them together. So, you have the R bar T0 and then each of the component has Xi ln Xi, where Xi is the molar fraction of the component. So, let us also do a quick example for calculation of chemical exergy of the mixture. Here you have a binary liquid solution of methanol and ethanol is given at T naught and P naught as 1 bar. The mole fraction of methanol is 0.60 and the chemical exergy already calculated is 1200 kilojoule per mole. Of course, if you want to calculate the chemical exergy of methanol, you can follow the previous process by making it in equilibrium with some reference substance. And then the standard molar chemical exergy for ethanol is 1400 and the mole fraction of ethanol is of course 0.40. So, let us take 30 seconds to do this problem. So, here it is again a straightforward calculation. So, for calculation of the exergy, you will do X of methanol multiplied by the epsilon methanol, which is the chemical molar exergy, plus X of ethanol and multiplied by epsilon of ethanol, which is your molar chemical exergy of ethanol. So, that is the part that is just because of the constituents. Then the part that is basically taking care of the work done. So, you have RT0, so you have 8.314 since it is in, okay, let me first write the formula. So, you have RT0 and then you will have Xi ln Xi. So, we have X methanol ln of X methanol plus X of ethanol and ln of ethanol, sorry, ln of X ethanol, which is the molar fraction. So, all you need to do is substitute and calculate. So, here we have methanol is 0.60 and the value is 1200 and ethanol will be 0.40. So, it is a binary mixture. So, your mole fraction of ethanol will be 1 minus 0.60, and epsilon of ethanol is multiplied by 1400. Then R is 8.314 kilojoule. So, you have to, because we are doing everything per mole, so we divide by 1000. T naught is 298.15 and X methanol is 0.60, ln 0.60 plus 0.40 ln 0.40. Okay. So, when you do all this calculation, your value should come out to be 1278 kilojoule per mole. So, that is the exergy of this binary mixture that may be an input stream into your process. So far, what we have learnt is all the ways we can think of exergy that is entering or leaving the system in terms of physical and chemical exergy. Physical exergy is really straightforward. So, let us look at the summary. So, the summary in we can do a thermal exergy calculation just by the temperature gradient. For physical exergy calculations, if you have gaseous component, we look at the thermal and pressure component. So, remember the first problem we did was on identifying the thermal and the pressure component separately. Then you can do chemical exergy calculation based on the chemical constituents. So, for any pure component, you know, if there is a reference, you can easily calculate is using that one formula. Then standard values of exergy for reference substance are usually provided, but if it is not provided, then you can go back to the formula for that calculation and calculate it for your input. For compounds that are not reference species, we saw an example of carbon monoxide calculation. The idea is that for all of those compounds, what you would do is you would find a reference species, write the reaction and then calculate the chemical exergy of that component. And then exergy of a mixture is simply the idea that you are doing some additional work to bring the constituents together. So, you have the part that is the contribution from the molar exergy of the constituent itself plus the part which is the contribution because of the total work done. So, there is a detailed book on exergy method for technological and ecological applications by Zargat, and that has been a standard book. So, if you have more interest in actually doing the exergy calculation, you can do use this book as a reference. For the purpose of use and sustainability, most of the exergy values are given, but we might also for materials that we are introducing new at different temperature and pressure, we might want to calculate it. So, when you want to include in LCA your exergy analysis, you calculate the exergy rate for streams when you are provided the physical and chemical composition. And also, since exergy represents the amount of work done, it is used as a quality of material proxy. So, in the next module, we will talk about using this exergy for evaluation of the processes for sustainability. The idea is that for lot of the stream which does not have an energy content, if you want to evaluate the thermodynamic sustainability, we actually go to look at the quality of material in terms of how much work was done to actually make that material that is used as an input in your process. And also when it is the output, that tells that how efficient is your process in actually converting the available energy to actual useful product. So, that gives an idea of that how second law is actually being used for thermodynamic sustainability assessment using exergy as a proxy metric. So, in next module, we will look at the exergy analysis for sustainability.